have the same number of elements. Okay? And Cantor proved in about 1870 or so that even the algebraic numbers have the same cardinality as natural numbers, same number of numbers. He also proved that real numbers are in fact much more. His proof landed him in a mental asylum because it was so revolutionary that people refused to accept. People like Poincare and Kronecker refused to accept that such a thing could happen. Okay? And so I'll give you the idea of it. So suppose real numbers could be counted. Suppose we know that rational numbers are the same as integers, the number of them. So suppose the real numbers also had same number as integers, right? So let us consider the numbers between 0 and 1. Real numbers between 0 and 1, right? They are all smaller than 1, right? And we can write them in binary, right? Now since they are in integers, they are all the same number as integers, I can list them down. For 1, I can write a first real number, I can write a second real number, I can write a third real number, I can write a fourth real number, I can write a fifth real number, right? So let us suppose that I write real numbers like this. Since they are smaller than 1 and they are written in binary, they'll start with a point. Let's say the first one is 0, 1, 0, 0, 0, 0, 0. Second one is 0.1000. Third one is 1, 1, 0, 0. And so on. Some way. I'm just listing down the numbers. There's some way I can list all these numbers. Right? Now, let us look at the following number. Okay? At the first number, I have a 1 at the first place. Right? So, I write 0. Right? Now it's different from the first number at the first place. So I know it's at least different from the first number. For the second number, I look at the second place. This also has a 1 key. So I change it and write a 0. Now it differs from the first two numbers. Right? For the third number, I look at the third place. It's a 0. So I change that to a 1. And so on. What is that? I'm creating a number that is different than every number I've listed. But how is that possible? I listed all the real numbers, but here we have a real number that is not the same as any of the ones I've listed. It's different from everything I've written down. How is that possible? That means that I cannot list real numbers. The real numbers are much more than rational numbers or real numbers. This argument is called Cantor's diagonal because you're basically taking the algebra into consideration. Right? So that is the real numbers. Now real numbers are nice. You could take squares, you could take powers, and you're still landing up in real numbers. You can do cube roots and things, and you're still in real numbers. But it's not all possible. There are still things missing. Most notably, you still don't have x squared equals -1. Because the way we define real numbers, the square of a real number is always positive. Right? So how can it be a negative? So what do? We have already filled up the real number. What do we do now? We need to create new numbers. Right? So we create something that we call an imaginary number. Let's create a number called I. I for imaginary. And we say that I squared is actually -1. Right? Then we can take multiples of this number. We can take square root of 3i. And now if we square this, that will give you square root of 9, -9. Right? We can take things like this. And that's a whole new line. Right? We have the real line and what we call the imaginary line. Now, we can take combination of these two numbers. We can take a real number and add an imaginary part to it and create a new number. And such numbers, which are combinations of a real part and an imaginary part, are called complex numbers. And complex numbers are nearly all possible. they allow you to do nearly everything out there. Every polynomial equation has to have a solution in complex numbers. So things are very, very nice. One thing that is important with complex numbers that you won't encounter in a very later stage is that you can add matrices on complex numbers. If you have a 2 by 2 matrix, you can say that the matrix acts on a complex number to create another new complex number. Okay? So suppose I have a matrix A, B, C, D. To make matters simple, I'm going to assume it has determinant 1. What does that mean? AD minus BC equals 1. Then we can define what is called the action of this matrix on a complex number Z. And what is this action that I'm speaking of? It sends Z to AZ plus B over CZ plus D. As long as CZ plus D is not 0, this is another complex number. Right? And what's funny about this? So, if you see, complex numbers form a whole plane. Right? You have one line like this, one line like this. If you take combinations, it's going to cover this whole plane. What this action does, under this constraint, is that if you take a number in the upper half, if you take a number here or so, it's going to remain in the upper part of the plane. It won't have a negative imaginary part once you do that. It might send it here, but it won't send it down. And this action is the basic thing for all modular forms and automorphic forms. This is the most important thing. We study this action and functions, what is called functions which have certain properties with this action. So this is a very important action that you can do on complex numbers. Okay? So that's complex numbers. And they are nearly all partial and stuff. But what if I want to explore more? What if I want more? Can I expand my complex number further? Do I get something? So what do my complex numbers not have? So for example, if you look at matrices, you know that A times B is not always equal to B times A in matrices, right? What if I want a thing like that in my complex numbers? Unfortunately, my complex numbers don't allow me to do this. Because of the constraints, the way we designed our complex numbers, AB will have to be BA. So if I want AB not to be equal to BA, I'll have to expand my complex numbers. I'll have to go even beyond. So here's one way of going beyond. There are many ways, but here's one important way. So I've already created one imaginary number, I. So how does it matter? I can create more imaginary numbers. So I'll create another number. 1, I, and since I'm using I, the next one would be J. Right? Now what conditions do I want? I want Ij to not be equal to Ji. Right? This is the condition I want. Right? So here's how we do this. We call Ij as K. I'll write this as equal to K. Okay? So we have a third number here, K. And this particular set that we do, we add conditions Ij equals negative Ji. Okay? So that it's not commutative anymore. Ij is not Ji. And I say R squared equals J squared equals K squared equals negative. This is a special condition. Originally, we had only I squared as negative 1 in our complex numbers, right? But I said, oh, how does it matter? I'll just add more numbers, 2 squared as negative 1. Let's see what happens, right? And I take numbers which are combinations of this. So, A times 1 plus B times I plus C times J plus D times such numbers. This kind of numbers are called Hamiltonian quaternions, and they are very important in physics and math. I think spin groups or something has to do with Quaternion algebra, something related to this. Okay? And automorphic forms, which is what I talked about, they also generalize to such numbers. So these are widely studied. So this is one way of expanding rational numbers to complex numbers to quaternions. But is there another way of generalizing rational numbers? Can we do something else? So what if I want to study a particular prime? What if I'm interested in the prime? What if all my world is concentrated on that prime? What if I want everything to be around that prime? So what if my numbers are more interesting to me if my prime divides them? And even more interesting if it divides it multiple times. Right? So suppose I take my prime to be 5. Suppose p is equal to 5. Right? Then I can create a new norm, absolute value. I create a new absolute value. How does my absolute value work? Have absolute value of a over b with respect to 5. How does it work? If I can write this as 5 to the k times a over p over q, right? Then the absolute value of this number is going to be 5 to the minus k. What does this mean? In a way, if your number is big, but it's divisible by 5 a large number of times, then it's actually closer to 0. In theory, you'd think that 125 is a very big number compared to say 1 over 5. But when I'm taking this absolute value, 125, what is the absolute value of 125? This is going to be 5 to the 3 times 1, right? So my absolute value with respect to 5 is going to be 1 over 125. Right? And what is going to be the absolute value of 1 over 5? Right? So my 1 over 5 is actually a bigger number than my 125. It seems counterintuitive, but that's how our distance works. Okay? So this is how we define the norm. Using norm is just absolute, another word for absolute value. Using this absolute value, we can create a new distance. How do you create a distance using an absolute value? Distance between 2 points A and B is just A minus B and absolute value of that. Here we are taking absolute value of 6.5. Right? That's the distance on my numbers. Right? So my numbers, when they are divisible by 5 more, they are getting smaller, and when they are divisible by 5, they are getting bigger. Right? Now I have a distance. What do? I have my rational numbers. We do the same process that we did to get real numbers. We complete our rational numbers. We take sequences and we try to fill those. Right? And what we get from that is called the p-adic completion of rational numbers. Okay? In this case, since I am dealing with 5, it will be written as q 5. Okay? This is with 5. With 3, it will be written with q 3. For a general prime, it's just written p. Right? So I have these. What is different? What is different from rational numbers or real numbers? What does it look like? How do these numbers look like? Right? So you have these. First thing you notice is every integer has absolute value less than or equal to 1. Why is that true? The way we define absolute value, when can a number have absolute value more than 1? When your k is negative here, right? Only then is your number going to have absolute value more than 1. But what does that mean? How does k become negative? Your b here has to have powers of 5. Right? Only then can your k be negative. You're pulling out powers of 5 and from the top and bottom, that's the total power. If your b has powers of 5, only then your k has chance of being negative. But what is the denominator of an integer? 1. It does not have any power of 5 or any prime for that matter. So for every periodic completion, all your integers have the property that absolute value of x is smaller than or equal to 1 if x is an integer. So we say, what's really special about integers? Let's look at all numbers which satisfy this property. They behave more or less like integers here. There's no special distinction between integers and these numbers. So we look at this set. This is what is our important set in this. This is the generalization of integers. And this set is written as C. These are called the periodic integers because they are the direct generalization. Right? So what do these numbers look like? Sure, I've created some funny numbers, but what do they look like and how do they behave? What are my things? So here's how a number looks like. A periodic number is summation I greater than or equal to 0, ai equal to I. This number belongs to Z. Because, well, I'm starting from greater than or equal to 0. So a1, I don't have any negative powers of my prime, right? So my absolute value is going to be greater. Oh, sorry, I forgot to mention one thing. So this periodic absolute value, this has one funny property. Usually, absolute value of a plus b is smaller than or equal to absolute value of a plus absolute value of b. Right? This is what we call the triangle inequality and things. This is how our absolute value works. Periodic absolute value is slightly stronger. It is what we call an ultrametric. Okay? What it satisfies is absolute value of a plus b with respect to a prime b. For every prime this is satisfied. Is actually smaller than or equal to maximum of absolute value of a and absolute value of b. What this means is that if you add the two numbers, they can only decrease. It cannot increase in absolute value. It has to decrease from at least one of them. It might be equal to its absolute value might be equal to one of them, but it cannot be more than both of them. Right? An example of this would be 4 plus 1 when you take the 5. What is 4 plus 1? This is 5, right? And what's it? What is its periodic absolute value? 1 over 5, right? This is going to be 1 over 5. But on this side, what is the absolute value? What is the absolute value of 4 with respect to 5? 1. Because 5 does not divide 4. It does not divide its numerator or its denominator. It divides its 0. So 5 to the 0 is going to be 1. So it's smaller than maximum of 1. And what is the absolute value of 1? 1. Because 5 is right? So that is an example where the absolute values are actually decreasing. Otherwise things are generally they are equal. Right? So because of that, here, as my powers of p increase, my absolute value is decreasing. If I add more powers of p, it's going to still decrease. It's not going to increase. Right? So this number has absolute value less than or equal to 1. So what are these numbers? What do these numbers look like? These numbers, they allow a few negative powers. Not all powers of p have to be positive. Some of them can be negative, but only a finite number. Now, if you look at it, what does it look like? What does this sum remind you of? Kind of. If instead of p, I was writing a 10. It was summation ai 10 to the I. What does this look like? What is of this form? Okay, sorry. Our ai's are between 0 and p minus 1. They are the digits in our thing, right? So they lie here. So in our case, our ai's would be from 0 to 9. So what does this thing remind you of? Natural numbers, normal natural numbers, the way we write it. So this thing is more or less like writing natural numbers to base p, right? They add in a similar way. You just add things. If it is more than p, you take a carry, you move it to the next place. The same way as you add integers, right? Instead of 10, we are dealing with a p. Why is this different than just writing numbers to the base p? What is different from writing integers to the base p and these numbers? When you write integers to the base p, right, your sum has to be finite. Why? Because if you take a bigger power of p, it's a huge number. You're going very fast to infinity. Right? Here, if you add a very big power of p,